So, hello class, no? Now we're going to conclude, no? And continue our discussion for method of consistent deformations, and specifically on this video, we're going to focus on multi-degree indeterminate frames, no? And just to give you a little insight, no? Frames are somewhat similar to beams, no? Kasi they also experience shear, no, and bending moment, pero the difference is of course the orientation, no. Ang beam kasi natin are purely horizontal or purely vertical, but for frames, no, it is a mixture of horizontal and vertical members, no. Minsan nga inclined pa, no, and at the same time, no, axial forces are also acting on it, no, and also the methods, no, of determining the deflection are, no, also different, no. And sa beams, no, we have lots of methods to choose from, no, when determining deflection. Pero as per our last discussion sa frames, no, we can only rely on virtual work method, no. So let me show you, no, how are we going to do it, no. So let's consider this example, no. You're given a frame, no, with members AB, BC, and CD. Member AB and member CD are vertical, no, with length of 5 meters, and member BC is 10 meters, no, acted upon by a uniform load of 30 kilonewton per meter, and a concentrated load of 50 kilonewton acts at point B. Now we are to determine the reactions, no, assuming that your EI is constant, no. So like what I said before, no, solving for the reactions of an indeterminate frame is somewhat the same, no, as solving the reactions for beams, no. It's just that the approach would be different, no. So first, what we're going to do is to remove, no, what we call the redundant, in order to make your frame statically determinate, no. So again, we can either choose to remove this one, the hinge or the pin reaction at point D, in order to make it a cantilever frame, no, or we can just remove the reaction, the moment here, no. We can remove the moment here and another of the reaction in order to make it simply supported. But for the sake of our discussion, no, I decided that we're going to remove, no, all the reactions at point D, no. Therefore, this is how it will look like, no. It will now become a fixed beam, no. So fixed frame rather, no, fixed frame. And then if we retain all the loads that originally acts on the frame, no, normally it will cause deflection, no. And we are to determine the deflection at the point where we remove the redundant, which is point D, no. And then we are going to let delta dx1, no, and delta dy1 be the deflection at point D due to the loads when the redundant at D is to be removed. No? Okay? Next, no? We remove all the loads. We remove these loads and then we replace it by a unit load, no? In which we're going to assume the reaction will be directed, no? So first, pag tinanggal natin yung load, no, mag-a-assume tayo na ngayon ng direction, no, for the horizontal and vertical reaction at D, no? And then yun ang i-apply nating unit load, no? So yan, no? So I decided to assume that our horizontal reaction at D will be at D will be going to the left. So therefore, I apply a unit load, no, horizontal unit load going to the left, no, and then I let FDX1 and FDY1 will be the horizontal and vertical deflection at point D due to the one horizontal unit load, no. So ulitin ko yung ginawa ko, no, nag-assume ako ng 1 unit load, and then of course this load will normally cause deflection, no, and ang deflection niya will be denoted as FDX1 and FDY1, no. Next, so I'm going to remove this load and then we'll replace it by our vertical load, and then I decided to assume that our vertical reaction at D will be vertically upward, so therefore I apply a single unit load upward, and then again due to this, no, it will deflect again, and then I decided to assume that your FDX2 and FDY2 will be the deflection at point D due to the vertical unit load, no. So therefore, our working equation now will be, no, delta dx1 plus fdx1 dx, no. So I will just add up all the deflections, no, at a certain point at a certain direction, no. So therefore, I will just add all the horizontal deflection at D and I will just add all the vertical deflection at D, no. So ito yung kinalabasan niya. Delta dx1 plus fdx1 dx plus fdx2 dy is equal to 0, no. The 0 at the end is just means na there will be no resulting deflection, no. Ibig sabihin, pag in-add ko lahat ng deflection, no, magka-cancel out lang siya. Okay? And delta dy1 plus fdy1 dx plus fdy2 dy will be equal to 0. Okay? And we're just going to apply the principles we've learned from theory 1, no, to determine the delta x1, delta dx1, fdx1, fdx2, delta dy1, fdy1, and fdy2, no. So let's determine your delta dx1 and delta dy1 first, no. If you can recall the virtual work method, no, what are we going to do is to make a virtual frame, no. So this is considered to be a real frame, no, acted upon by the original loads, no, the 30 kilonewton uniformly distributed load and the 50 kilonewton concentrated load at point B, no. So what are we going to do in order to form a virtual frame, no? We remove these loads and apply a unit load or a unit moment at the point in which we're going to determine the slope or the deflection, no? In our case, no, we are going to determine the horizontal and the vertical deflection at point B, no? So therefore, we apply a horizontal unit load 1, no, kung hahanapin natin yung horizontal deflection, and vertical unit load na 1 kung hahanapin naman natin yung vertical na deflection, no. So ngayon ang deflection natin will be, no, 1 multiplied by delta, no, is equal to the integral of the moment equation for the real system, the real frame, multiplied by the virtual moment, no, moment or the moment for the virtual frame, multiplied by dx over ei. No, if we are to determine the slope at d naman, no, we apply, no, unit moment, no. So 1 kilonewton meter multiplied by theta is equal to the integral of the virtual moment, no, the real moment dx over ei, no. So this is our derived equation, no. And as you can see, no, meron na tayong ginawang virtual frame, no, or rather, no, we're just going to utilize yung inassume nating direction for the horizontal and the vertical reaction at D, no, instead of just making another moment, no, instead of making another virtual frame, no, kasi nga kung gagawa pa tayo ng sobrang daming virtual frame, no, kagaya nung sa taas, no, medyo malilito pa tayo, no. So yung ating assumption ng horizontal and vertical reaction, no, yun na lang ang gagamitin natin as our virtual frame, no. So therefore your delta dx1, no, is equal to the integral of the moment ng real multiplied by the virtual moment for x, no, dx over ei, and delta dy1 is equal to the integral of the moment, no, multiplied by the virtual moment for y, no, dx over ei, no. So if you can recall this 2 unit loads na ginawa natin, no. So ito na yung gagamitin nating virtual moment in order to avoid much confusion, no, kasi nga mahaba din ang magiging process natin, no, for determining the moment equations for frames, no. And those, meron na tayong delta dx1 at saka delta dy1, no. Now we're going to determine your fdx1 and fdy1, no. So fdx2, fdy2. In fdx1 and fdy1, no, we are aware na your real frame, no, is also the same as your virtual frame, no. So therefore, no, ang fdx1 natin, fdx1, no, will just be equal to the integral of, no, mvx, no, times, dahil ang virtual natin for this, no, in determining the horizontal deflection is just the same as the real, no, we just square this one, no, multiplied by dx over ei. And in fdy1, no, this is the integral of, dahil ang real natin is the horizontal and ang virtual natin is vertical, no, we just multiplied mvx multiplied by mvy dx over ei, no? So we have f dx1 and f dy1, no? So let's move on to f dx2 and f dy2, no? So ang f dx2 natin, no? Ang real natin is the vertical unit load, pero ang real natin rather, no, tong considering this is the horizontal unit load. So therefore yung fdx2 natin will just be equal to fdy1, no, fdx2, let's cross this out, no, fdx2, no. And sa y2, yung real natin is the same as your virtual, no? So therefore this will just be the integral of mvy squared dx over ei. Okay? So we're going to individually determine the moment equations of each frame that we made, no? Yung the original na primary frame, no? Next na with original loads, no, that we have, and the primary frame, no, the with individual units loads that we need, no. But we first need to tabulate the following, no, in order to avoid confusion, no. So we make a table, no, concerning individual members, no, of the frame, no. If you can see from the figure, no? So if you can see from the figure, we have, no, AB, no, BC, and CD, no. And the next, we're going to determine the limits, no, for our integration later, no. The limits, of course, is the length of your member, no, of your frame member, no. So from AB, the limit will be from 0 to 5, no. BC will be from 0 to 10, and then CD will be again 0 to 5. Okay, no. For your origin, no, of course, we need to determine the point, no, saan tayo magsisimulang magsukat ng moment, no. So if you're going to, in choosing the origin, you need to choose, no, you need to choose the point wherein the moment, no, should be at the minimum. Ibig sabihin, dapat ang moment mo as much as possible 0, no. So no, in AB, no, in member AB, no, we can either go from A to B or from B to A, no. Since we have a 50 kilonewton concentrated load here, no, and it will be really complicated to minimize the computation there. We can set your origin at point A, no. Now at point D, no? So this is just the same. At point D, no, we know na there's no load acting on it, no? So probably there will be no moment. So we can just set the origin at point D. And at C, no, we know that the moment is much smaller at C, no, rather than at B. So therefore, we can just choose point C as our origin. No? So later on, we're going, the moment equations that we need are the moment at the individual members due to the original loads, no? The MVX due to the horizontal unit load, and MVY due to the uh, vertical unit load. Okay? And in order to determine this individually, we are going to go back, no, to what we've learned again from our theory 1, no, which is frame analysis. So for our frame analysis, no, allow me to classify this as frame number 1, no, the primary frame with our original loads, no. Next, frame number 2 for the primary frame, no, with the horizontal unit load, and frame number 3 for primary frame with vertical unit load, no. So let's analyze frame number 1 first, no. Okay, so for frame number 1, no, no, let's solve for the reactions first, no. You know, we are all aware that there are 3 different reactions for frame number 1, no. We have the vertical reaction, let this be your a sub y, no, and let your vertical reaction be a sub y, no, your horizontal reaction be your a sub x, and moment at a be m sub a. Okay, we will be able to solve that, no, using our calculator, no. Your a sub x, no, is just the opposite of your 50 kilonewton horizontal load, no. This is 50 kilonewton, no, and your ay is just the opposite of your uniformly distributed load, no, the resultant of your uniformly distributed load, 30 multiplied by 10, no. So this is 300. Your moment at A, no, is just the product, the sum of the moment due to the 50 kilonewton load and the 30 kilonewton per meter uniformly distributed load. So therefore that is equal to 50 multiplied by 5 plus 30 times 10 times 5. No, this is equal to 1,750 kilonewton meter, no. So now we all have the reactions, no. We separate it member by member and joint by joint, no. So first we are going to isolate your member CD, no. So let's isolate member CD, no, and let's isolate your joint C. Then let's isolate your BC. Isolate joint B. And then isolate member AB. So let this be your A. This is your B. This is your B. B, this is your C, C, no? C, and this is also your D, no? So the technique for doing frame analysis is, oh, let's put all the loads first, no? Let's put all the loads, no? Our loads and all our reactions, no? So then your moment at A again is equal to 1750 kilonewton meter. Okay, so the technique for doing frame analysis is you start, no? You will start at the point wherein your moment is at the minimum, no? So we all know that we don't have any load, no, present at member CD. So we can start here, no? So we know that member CD, no? We know that there is no shear here and there is also no moment here, no? No shear and also no moment. No shear, and then again, no moment. Okay? Then so therefore we don't have any shear here and we don't have also moment there. Okay? So we can now write we can now update our table, no? So here, no, your member CD, your M is now equal to 0. Okay? Next, after the member CD and our joint C, we're now going to proceed at member BC. And as you can see from our table, we've started at our origin is at point C. So therefore, we're going to measure our moment starting from letter C, no, going to B, no, with the limit from 0 to 10. So therefore, we're going to write your moment equation, no, in terms of x, no, starting from letter C, no. We can be able to say that your moment equation from C going to B will now become, no, from here again, no, 30 no, multiplied by x multiplied by x over 2. Okay, no? So that is your moment equation, no, at member BC, no, with origin at point C, no. Next, what sign convention are we going to use pala, no? So for the sign convention, no, we should be considerate of this. We are going to assume, no, let's try to isolate this point, no. Okay, so if we isolate that point, no, So we have your uniformly distributed load here, no? Therefore, we can be able to say that this is your shear, and you also have your moment here, no? Okay. No, so you have your moment here, no, and this is with respect to this is from left going to right. But how are we, if you can recall design convention for bending moment, no, if you can recall design convention for bending moment, no, this is how it should be done, no. If your moment is causing an upward bending, no, kung napapangiti niya yung beam mo, no, your bending moment is positive, no, if it makes your beam frown, no, kung napapasimangot niya, no, your bending moment is negative, no. So nakita nyo naman, no, that your moment, no, is making your beam frown. So therefore, we can just say that your moment equation here is negative, no. Okay, next, no, we're okay with your member BC, no. Our next moment equation, the next moment equation that we need to find is the moment equation here at member AB. But of course, we need to complete first, no? We need to determine the shear and bending moment at joint B, no? So let's fill this up, no? So yan, no? So at joint B, no, you have your shear here, no? So your shear at joint B, no? Your shear at joint B will now be 30 times 10 times 30 times 10, no? This is equal to 300, no? And your bending moment naman will now become, no, 300 multiplied by 10 multiplied by 5. Rather, 30 multiplied by 10 multiplied by 5. This is equal to 1,500. Now, if you have your 300 here, of course, nga pala, I isolated the joint, no? Kasi we have a concentrated load here, and we can avoid confusion by isolating the joint itself, no? So we are going to assume that this is a very small distance between the applied load and the applied uniformly distributed load, no? So parang sobrang liit lang na distance ito. Okay? So if you have a 300 kilonewton shear here, no, of course yung kabaligtaran lang niya na direction, no, 300 kilonewton. And if you have a 1,500 kilonewton meter moment here, no, of course kabaligtaran lang din nun, 1,500. And if you have a 300 kilonewton here, you will also have 300 kilonewton load here, no? So 300, no, and this will also become 300. If you have your 1,500 here, 1,500, no, this is clockwise, so of course you will have your counterclockwise moment here now, which is also the same magnitude, no. And of course your 50 kilonewton here, no, you will also have an opposite 50 kilonewton here. Also, you have your 50 kilonewton opposite here. No? And then a moment again. No, this is counterclockwise moment. So therefore, you will also have your clockwise moment here. No, this is equal to 1,500. This is equal to 50. No? Okay? No? You need, no? What you need to, what your goal should be, no? Dapat, this member, in order to tell whether your analysis is right or wrong, no? This member should be on equilibrium, no? So let's try, no? If we do summation of moment at A, no? If we do summation of forces at X, no? This is 50 and that is 50. So therefore, that is in equilibrium naman, no? If this is 300, no? Your 300 is also the opposite. No? If we do summation of moment at A, no? You have a 1,750 kilonewton moment here, no? So negative 1,750 plus 1,500, no? Plus 50 okay, negative 1,750 plus 1,500 plus 50, no? Multiplied by 10, no? Okay, so again, no? Let's try to repeat that again, no? So 1,750 no, minus 1,500, no, negative 1,750 plus 1,500 plus 50 multiplied by 5 meters, no? That is equal to 0. So therefore we have an equilibrium here. Pero the moment equation, we measure your moment starting from point A, no, going to B, no? So this is your X. Your moment equation now will become, no, 1,750, no? Again, no? If we try to orient your frame member like a horizontal beam, no, we can tell that your frame here undergoes, no, upward bending, no, or it is making your frame member frown, no? Pinapasimangot niya yung frame member mo. So therefore, no, your moment at member AB starting from point A is negative 1,750 plus, no, 50 multiplied by X. Okay, so now your moment equation at your frame number 1 is now complete, no? So let's proceed with your frame number 2 and frame number 3. Okay, so let's proceed with frame number 2, no? We determine the reactions first, no? So this is your horizontal unit load, no? If we do summation of forces X, no, we will be able to know that your AX is just the opposite of this unit load, no, which is also equal to 1. No, if we do summation of forces Y, we will be able to know that AY is equal to 0. If we do summation of moment at A, we will be able to know na your unit load here will pass through point A, so therefore your MA is equal to 0. Okay, next thing that we do is to isolate all the joints and all the members, no? So we isolate member CD, no? Isolate joint C, isolate member PC, isolate member B, isolate member AB. We put all our reactions, no? So 1 kilonewton to the left and 1 kilonewton to the right, no? At joints D and joint A respectively, no? So if we start again at member CD, no? Since we have 1 kilonewton load here, no? We will be able to know that your at joint C, no? We have an opposite force of 1 kilonewton, no? And if we multiply this 1 kilonewton load, unit load, by the length, which is equal to 5, no? 5 meters, no? We will be able to know that there is also a moment at joint C equal to 5 kilonewton meter, no? And the direction, since this is clockwise, no? The moment at C is just the opposite, just acts at the opposite direction, no? And this is counterclockwise at C, no? Therefore, at joint C, a very small distance going to D, no? Meron tayong clockwise moment of 5. And then also, we have an opposite of 1, no? So this is going to the right na 1 kilonewton. So meron tayong going to the left na 1 kilonewton dito, no? A very small distance from joint C going to joint D, no? Kapag joint C naman going to joint B, no, at a very small distance, no, kung ito ay 5 kilonewton meter na clockwise, we have a 5 kilonewton counterclockwise here. Kung meron tayong going to the left na 1 kilonewton load dito, meron tayong 1 kilonewton going to the right. Again, no, dito naman tayo sa member BC, no, at joint C, no, meron tayong to the right dito. So therefore opposite, no, may 5 kilonewton na counterclockwise, therefore 5 kilonewton na opposite lang. And then at joint B, point B, no, may 1 kilonewton tayo dito na to the left, magkakaroon tayo ng 1 kilonewton to the right dito. Then we have a 5 kilonewton na clockwise, therefore 5 kilonewton na counterclockwise, no? Going to joint B, meron tayong 1 kilonewton na to the right dito, so therefore 1 kilonewton to the left, no? So counterclockwise na 5 kilonewton meter, so therefore may clockwise tayong 5 kilonewton meter dito. Then again dito, dahil meron tayong to the left na 1 kilonewton unit load, meron din tayong 1 kilonewton left dito. Then meron tayong clockwise na moment, counterclockwise na moment with the same magnitude. So dahil meron tayong to the right dito, meron din tayong to the left dito. 5 kilonewton na counterclockwise, 5 kilonewton na clockwise. Okay. And dahil dito meron tayong counterclockwise na, meron tayong to the left na load dito. Of course, yung reaction natin, no, understood na going to the right, no? You can also check by doing equations of equilibrium, no? Okay, for the moment equations naman, no, start tayo from at member CD, no? So at member CD, no, ang origin natin ay at point D, no? Kapag sinukat natin, pag nag-consider tayo ng point within joint CD, Now we assume that the distance is x, no, starting at point D. Now we will be able to know that our moment equation, no, is equal to, no, 1 kilonewton load multiplied by x. Pero for design convention, no, dahil kung inassume natin na ito ay horizontal, no, ma-realize natin na parang pinapasimangot niya yung frame member mo. So our MVX now at joint CD is equal to negative x. Now proceed at member BC naman, no? Our origin is now at C, no? This is your X, no? We have a constant moment of 5 kilonewton meter, no? Until the point B, no? Na magka-cancel out yung moment mo. So therefore, your MVX is 0 minus 5. Next. Okay, next. Our AB naman, no? Member AB, no? Your X will be measured from point A, no? And we only have 1 kilonewton load here, no? 1 kilonewton reaction. No? So 1 multiplied by x is equal to x, but the direction, no, but the bending, no, it causes the beam to frown. Pinapasimangot niya yung beam mo, so therefore your MVX now will become negative x. So now we're almost complete. Let's analyze naman frame number 3. Next, we're going to analyze, no, frame number 3, no, which the unit load is vertical. First, we determine the reactions, no. If we do summation of forces X, we will be able to know that your AX is equal to 0. Your AY will just be the opposite of your vertical unit load, which is equal to 1 kilonewton, and then your moment at A will just be the opposite of your 1 kilonewton, no, which is causing counterclockwise moment. So therefore this is clockwise, no, 1 multiplied by the length, no, which is equal to 10. 1 times 10 is equal to 10. Okay, next we isolate all the joints and then all the members, no. So we isolate member A, AB, no, joint B, okay, member BC, joint C, and then member C. We put all the loads that we have. We have a 1 kilonewton downward and then a 10 kilonewton meter counterclockwise. 10, and then this is 1, and then we have an upward load of 1 here. Okay, so of course, we start again from D going to C. If we have a 1 kilonewton going upward, we will be able to know that we have 1 kilonewton going downward. Then the opposite again. No, this is 1. They are both 1. No, we have a 1 kilonewton upward here. No, so therefore we will have downward 1. Downward, upward. And then downward again. 1, 1, 1. Okay? That is using the principles of equilibrium. No, this is also equal to 1. No, this is equal to 1. Okay? Oh, rather, mali. I made a mistake here. Now we erase this one. This is it's true direction. Okay, this yan 1. and then this is equal to 1. Okay, next that we're going to do is to determine is to next, from C going to D, we don't have any transverse load here, so therefore there will be no moment equation here, but here, point C going to point B, if we measure okay, if we measure our we determine the moment at any point from C going to B, our origin from point C, denoted as X, we will be able to know that our moment equation is equal to X, but at X is equal to 10, our moment at point B will be equal to 10, this is counterclockwise, so of course we will know that this is clockwise, this is clockwise, this will become counterclockwise, this is counterclockwise, this is clockwise again, then this is clockwise, this will become counterclockwise again. Okay, this is 10. Okay, next, again going back, we don't have a moment equation here, so therefore from the table this will become 0. Okay, then at member B, BC, if we measure your moment from point C going to B, our moment equation is equal to X, but the direction, as per the direction naman, we know na the 1 kilonewton is causing the beam to smile, pinapangiti niya yung beam natin, so this is positive. Okay, next, at member AB, if we measure your moment from point A, this is the distance is assumed to be X, you'll be able to know that your moment equation, is equal to 10, 10 minus rather, that is just equal to 10, but what would be the direction, so if the direction that we use, of course, the orientation that we use on the previous beam of the previous frame members, should be the same as dito sa frame number 3. So kapag ginaya natin yung orientation ng mga frame kanina, makikita natin na pinapangiti niya yung frame member. So therefore, this is positive 10. Okay, that will be, so our table is now complete. Let's proceed with determining the deflections. If we can refer to the following formula, we will be able to solve for delta dx1, delta dy1, f dx1, f dy1, f dx2, and f dy2. So let's input everything using our calculator. So m, for delta dx1, this is equal to the integral of the product of m. What is your m? Don't forget, we are pertaining to the sum, no, of the integral of m multiplied by m vx multiplied by dx over ei of members AB, BC, and CD. No? So, let's do it. No? So, the product of m, your m at member AB is equal to negative 1750 plus 50x multiplied by negative x, no, from 0 to 5 plus the integral of, no, this is negative 15x squared, negative 15x squared multiplied by negative 5 from 0 to 10 plus the integral of 0. No, this is already 0. So we can just leave that. Okay? So your delta dx1 now will become, no, 44791.67 or 134,375 over 3ei. Okay, next, your delta dy1 is equal to the integral of, no, m, the moment equation, negative 1750 plus 50x multiplied by mvy, no, which is equal to 10 from 0, from just 0 to 5 plus the integral of, no, negative 15x squared multiplied by x from 0 to 10. This is just equal to negative 118,750 over ei. Next, we again next, okay, we try to 750 plus, I'll recheck this again. Let me recheck it again. 50x multiplied by 10 from 0 to 5 plus the integral of negative 15x squared 15x squared multiplied by x from 0 to 10. That is equal to negative 118,750 over ei. Okay, next. Okay, next we solve for f dx1, f dy1, and f dy2. Okay, f dx1 is just equal to integral of x, no, x multiplied by x squared from 0 to 5, no, plus integral of 10 from 10 squared rather, mali, no, times negative 5 squared from 0 to 10 plus the integral of negative x squared from 0 to 5 again. This is equal to 1,000 over 3 EI. Next, the f dy1, which is also equal to f dx2, integral of the product of negative x times 10, no, from 0 to 5, plus the integral of negative 5 times x from 0 to 10. This is equal to negative 375 over EI. No? Next, integral of 10 squared from 0 to 5 plus the integral of x squared from 0 to 10. Your f dy2 is now equal to 2,500 over 3EI. Okay, next we going back now to your working equation, no? So we place all our solved values, no? We place all our solved values now here, no? We place all our solved values to solve for your dx and your dy. So now, we all have the 6 deflections, no? So we input everything on our working equations, no? So delta dx1 is just equal to 1,34,375 over 3EI plus, no? F dx1 is just equal to 1,000 over 3EI, no? Dx plus f dx2, which is equal to negative 375 over EI, no? Multiplied by dy is just equal to 0. The next, we have your delta dy1 negative 118,750 over EI plus next f dy1, which is equal to negative 375 over EI dx plus 2,500 over 3EI dy is equal to 0. No? So we input everything on our calculator, mode 5.1. No? So 1,000 over 3. All the EI will be cancelled, by the way. Negative 375. No? Negative 134,375 divided by 3. The next, negative 375, 2,500 divided by 3 EI, then this will become positive 118,750. So your values for D sub x is equal to 52.53 kilonewton. No, our assumed direction is correct. Next, dy is just equal to 166.14 kilonewton, no? So both are positive, so therefore all our assumed directions are correct, no? So we can now, from our original figure, we can now place your 52 and now rather your 166.14 14 kilonewton, and then your 52.53 kilonewton. So 166.14 and then 52.53, no? So how are we going to determine our remaining reactions, no? Your moment, your horizontal reaction, your vertical reaction, and your moment at A, no? So let's refer to all our primary frames, no? So referring on your primary frames, no? So a you have your primary frame subjected to the original loads, no? And then we're just going to add all the reactions due to the solve reaction. We are just go on the unit load here, on the horizontal unit load, since tama naman yung direction na inassume natin, we're just going to multiply this by d sub x. Yung sinolve nating d sub x, multiply natin dyan. Now we're going to multiply everything here by d sub x. Next, sa vertical unit load, we're going to multiply everything by d sub y. No, so all our values we're going to multiply by d sub y. D sub y times d sub y. So therefore, and we're going to add everything. No, so from the primary beam due to the original load, no, and then we're going to add these two loads, no? So therefore, what we're going to do now, let's clear this, no? I-add natin yung reaction na to plus reaction na to na i-multiply lang natin ng dx plus yung reaction na to i-multiply lang natin ng dy. Okay? So unahin natin yung horizontal reaction at A, no? A sub x. So going to the left, assume to be negative. So negative 50, no, plus 1 times dx plus 52.53 plus 0. Therefore, your remaining reaction is 2.53. Now this is going to the right. 2.53. Your AX is equal to 2.53. Next, AY naman tayo. We add 300. So 300, no, plus 0 minus, dahil pababa to, minus 166.14. Therefore, your reaction naman at A, vertical, is equal to 133.86. For the moment naman, no, so assume that all clockwise moments are positive. This is negative 1750, no, plus 0 plus 10 times your dy, 166.14. This will be equal to negative 88.6, no, still counterclockwise. So counterclockwise, no, so 88.6 kilonewton meter. No, so here are your reactions, no. So that ends our sample problem for frames. And that ends our video, no. Thank you for tuning in, no. Don't forget to like and subscribe, no, to be updated of the announcement, no, as well as check your Blackboard din. no? And also, if you have any questions, don't forget to approach me, no? Uh, by leaving comments below, no? Or just message me, no? On any other means like social media or also the Blackboard messaging, no? And for the next video, no, we're now moving on to three moment equations. No? See you.